Okay, let's jump right into this explainer. We often think of chemistry as this tedious list of equations you just have to memorize, right? But it's really not. It's actually an incredibly dynamic, highly visual language that literally maps out everything around us. So today, we're going to focus entirely on the visual style of molecules, how we draw them, how we track their motion, and really, how these invisible blueprints shape our entire world. Let's get into it.
Here's our roadmap for today. We'll kick things off with visualizing the invisible, then move into the blueprint of molecules. After that, we'll look at the choreography of the electrons, try to solve the benzene ring mystery, and finally, wrap up with chemistry in everyday life.
All right, part 1, visualizing the invisible.
Okay, so you probably already know about the invisible forces at play in chemical bonds. But visually, how do we actually map them out? Well, we can picture ionic bonds as rigid magnetic attractions that just lock into place. Covalent bonds, on the other hand, are more like highly conjoined fluid spheres where the valence electrons are intimately pooled together. To truly read the universe, it's absolutely all about how we visualize that sharing.
Moving right along to Section 2, the blueprint of molecules.
So we all know the octet rule, but I want you to think of it as the core visual alphabet for drawing chemical structures. Carbon anchors our map with 4 bonds. Nitrogen likes 3 bonds and keeps 1 lone pair. Oxygen demands 2 bonds with 2 lone pairs. And halogens, like fluorine, they take 1 bond and 3 lone pairs. Once we start viewing this as a strict visual grammar, rather than just, abstract math, drawing complex molecules becomes as logical as connecting the dots.
And this grammar directly maps out saturation, too. Visually, a fully saturated alkane is packed completely tight. There is literally no room for anything else to attach. But an unsaturated alkene, that visually holds tension in those double bonds. They act exactly like loaded springs, just ready to snap open and accept more atoms.
Now this is where it gets really cool. Look at how an electrostatic map perfectly visualizes the unequal sharing of electrons. When a bond is polar, the map shows a physical, charged tug of war. Those deep red regions, they're electron-rich and negative, while the blue and green regions are positive. This uneven, bumpy terrain is exactly what dictates how molecules will physically collide and react with one another.
That brings us to Section 3, choreography of the electrons. To really choreograph chemical reactions, chemists use a technique called arrow pushing, and it is strict, but it's super elegant. Your double-sided arrow has to always start at the electron source, the nucleophile, and point exactly to the electron sink, which is the electrophile. You are essentially visually tracking the flow of electrons while meticulously conserving the overall charge.
And seeing this flow beautifully illustrates the danger of a really common visual mistake, hypervalency. If you draw an arrow incorrectly pointing right at a carbon atom that already has 4 bonds, the result is a carbon with 5 bonds, and that completely breaks our fundamental visual grammar. Honestly, you kind of have to see the wrong way to truly appreciate the elegant right way, where the arrows carefully track the electron flow, breaking one bond to form another, and beautifully conserving the overall charge.
Tracking these visual arrows clears up some major misconceptions, too. Take condensation. It doesn't mean a molecule physically shrinks. Visually, it shows 2 compounds combining and dropping a water molecule. And reduction? That simply means adding hydrogen across a double bond. Actually, scratch the idea of shrinking entirely. It's just a highly specific atomic choreography.
Let's dive into Section 4, the benzene ring mystery.
The visual journey of the famous benzene molecule reads literally like a 200-year historical detective story. It kicked off in 1825 when Michael Faraday isolated it. He actually made a slight math error that led him to incorrectly call it bicarburate of hydrogen. Decades later, Auguste Kekule used those new valency rules we just talked about to finally draw benzene as a ring with alternating double and single bonds. But the definitive visual proof? Wow, that didn't arrive until 1929 when Kathleen Lonsdale used groundbreaking hand-calculated X-ray crystallography to prove benzene was a perfectly flat hexagon.
So, how exactly did Kekule come up with that ring structure way back in 1865? Well, legend has it that the incredible breakthrough came to him in a dream. He described staring into the fire and seeing atoms just gambling before his eyes, twisting in a snake-like motion, until suddenly one of the snakes seized hold of its own tail. This wild, hypnotic vision of the Ouroboros gave birth to the foundational ring structure of benzene. Pretty amazing, right? Now, the absolutely crucial point here is that while Kekulé's dream was a massive leap forward, later quantum theory proved his alternating double bonds were actually slightly off. Kathleen Lonsdale showed the bonds were all exactly 1.42 angstroms long, which is right between a single and a double bond. Benzene actually features a highly stable, delocalized pi system, so the electrons aren't stuck in static double bonds. They're floating in a continuous shared ring above and below the molecule. This visual reality perfectly explains why benzene is incredibly stable and stubbornly resists addition reactions.
Finally, Section 5, Chemistry in Everyday Life.
Looking at these complex structures, they might seem a bit intimidating at first, but they use the exact same visual grammar we've been tracking today: the rule of 8, the specific bond counts, the lone pairs. Chemists use this very language to synthesize the medicines sitting in your bathroom cabinet right now, things like Flonase, Lipitor, and Paxil. By understanding these blueprints, you are basically learning to read the matrix of modern medicine.
And it goes way beyond medicine. From the moment you wake up, you are interacting with this unseen architecture. The foaming of your morning shampoo, dictated by the long organic chain of sodium lauryl sulfate. The vibrant orange of your carrot, visually produced by the specific double bond structure of carotenoids. The hydrocarbons you pump into your car, the polyethylene polymer shaping your water bottle, and the OLEDs illuminating the screen you are looking at right this second. Organic chemistry is for sure the invisible architect of your lifestyle.
Even the aging of your skin is a highly visual structural mechanism. When UV light hits your skin, it acts like a microscopic wrecking ball, creating free radicals. Visually, these are chemical species with an unpaired electron, making them frantically reactive as they try to steal an electron from your healthy cells, which causes damage. The solution? Antioxidants in your skincare and food. Their specific molecular blueprints allow them to step in and safely hand over an electron, completely neutralizing the free radical and stopping the damage in its tracks.
So, the next time you look out at the world, I want you to remember that beneath the surface of literally everything you touch, taste, and use is a fascinating structured dance of atoms just waiting to be seen. You now have the basic visual grammar to start reading the blueprints of the universe. So, I'll leave you with this. How will you use this language to decode the world tomorrow? Thanks so much for joining me on this explainer, and keep exploring the invisible.